If you haven't done so already, just pause the video now and make sure you've read the question. Okay, so first things we're going to do are put on the forces. So the weight of each of those boxes, the tension in the rope, so putting that weight up and pulling down on that pulley there, pulling left on the pulley there, and the rope pulling that block along. The acceleration of the system, this block is accelerating to the right, and we know it's inextensible. The acceleration must be the same in both. This block is accelerating downwards. And the one other force to include is the friction force, so the 0.08 G friction, which opposes the motion. And then we're going to do F equals ma at each of these blocks, because we've got the same T, the same A, but different other aspects. So T, which is the force accelerating it to the right, minus the friction is equal to the mass times the acceleration, which for the moment is A. At B, we take down as positive because that's the direction of acceleration. The weight or the force down is 0.8 G minus the tension, which is holding it back up, equals mass times acceleration. We have equation 1 and equation 2, so we're going to add the two of them together. The t's will cancel out, so we've got positive t there, negative t there. 0.8 G minus that, add those together, 1.2a. So acceleration is 0.72 over 1.2. Let's give ourselves that in terms of G, and then we can round it to SF as well. Then part B is asking us how long does this block take to hit the ground. We're told in the question that it's 0.5 meters above the ground. So that distance there is 0.5. So basically we want to know how long does a block starting at rest, so we're told that, accelerating at 0.6 G, take to travel 0.5 meters. S is ut plus a half at squared. U is 0, so this term disappears. Half times A is 0.3 G, and then t squared. Then we're solving that for t. .41 seconds to 2SF. Part C, and this is a really, really interesting type of question that comes up all the time with pulleys, is when you have to look at, so I've just stopped the writing just so you're listening, you have to consider two different bits of motion. So like until the string snaps or until such and such hits the floor. So it's like the initial acceleration, then something changes, then it's going to decelerate, then it's going to stop. Okay, so these two stage ones are really, really important. So we're looking at the total distance travelled by A before rest. So there's two parts, like I said. Part 1 is until B hits the floor. So until that block on the right hand side travels that distance and hits the ground. Whilst that's happening, A is going to be moving across. And then after B hits the ground, A is going to have a velocity and it's going to slowly, slowly decelerate until it stops. We know that B is travelling 0.5, therefore A must be travelling 0.5 across the top. So that distance is fairly straightforward. What's important to us is what is the velocity that A is travelling at when B hits the ground. Okay, so it accelerates, it speeds up, and it has a velocity. B hits the ground, then it slows down, then comes to rest. So we need to know what is that velocity at the point when B hits the ground, because that will determine how long it takes for A to slow back down and come to rest. So we know the velocity that the system was travelling at when B hits the ground was 2.42 meters per second. So after B hits the ground, the string goes slack, i.e., so let's see what that looks like. So originally this was being pulled along, then B hit the ground, so then the string goes slack. So the only force, so there's no longer a tension in here, the only force is the frictional force on A. So we need to know, okay, well it was travelling at this velocity, now the only force on it is that. So the question is, how long does that take to stop moving? So it had a velocity, force goes slack, so it slows down, and then stops. The only force on it now is 0.08 g to the left. Mass is 0.4, so the acceleration, rearrange that, is 0.08 over 0.4. May as well keep it in terms of g for now. Always, where you can, leave your answers in terms of g. So the acceleration is g over 5 to the left. That's not just me pointing at the answer, that's me showing that the acceleration is in that direction. Okay, or it's deceleration, effectively. So S is the thing we want to work out. We know we want to get to the point where until it stops moving. Initial velocity, so we're just looking at Suvat here for after B has hit the ground. We're calling right positive, therefore this acceleration is negative because the acceleration is to the left. V squared is u squared plus 2as. Final velocity is 0, so we want to know what's the distance until it reaches 0. That's u squared, which is the speed at the instant that the B hits the ground. We know the acceleration. We actually know u squared has come from up here. So again, rather than using the rounded value, let's use the original value, which is going to be 0.6 g. Okay, if you simplify that, you get 0.6 g. And then it's a case of rearranging this to get s on its own. So we'd subtract that over. In fact, let's just show where that comes from.